Hey there, I'm Nix, and this is part 2 of solving the rotate array problem on the LeetCode website. Still solving this problem in the C++ language, and still giving you a detailed explanation of the entire process, through the planning of the algorithms, to the coding of it, to looking at its time and space complexities, as well as the LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back, and after a busy week, I am finally able to get back into the swing of things and continue on solving the rotate array problem in more ways. So if you haven't already done so, I would suggest watching the part 1 video of this problem, because that introduces it and goes over some initial ways to solve it. This video is a continuation on that, so as a result, we're just going to get straight into the swing of things. Now, for a third solution of this problem, we know that we have to get some of the values that appear at the end of the array at the beginning, and then of course the beginning values at the end. And one really simple way to do that, albeit with all of the values not in their correct place, is to just completely do a reversal of the entire array. So instead of, say, bringing in my handy-dandy whiteboard, instead of this initial array that we're given, we completely reverse it, and we now have this array. While we do have the end numbers at the beginning and the beginning numbers at the end, they're of course not in the right place. However, if you look at it, say from the beginning of the array up until right before k, we have the numbers 7, 6, and 5 present. And 7, 6, and 5 are supposed to be there, but they're in reverse order. But that means that all we'll have to do is call a reversal of this section of the array, and then 7, 6, 5 becomes 5, 6, 7. And then those numbers are exactly where they should be. In a similar fashion, the section of the array from k on to the end of the array is also in reverse order from what it should be. So if we reverse that section again from its initial reversal, we will have 1, 2, 3, and 4 all in their rightful places, and our final answer is correct. So in order to do this, we just need to reverse the array 3 times in 3 different ways. The first way, reversing the entire array, and then 2 more times, reversing only specific sections of the array. Now, of course, C++ has a built-in reverse function to do just that. But where's the fun in that? Why don't we do this from scratch, especially since it can be a very easy scenario in a technical interview to find yourself in a position where, yes, this extremely useful, already in existence method is in existence, but you can't use it for solving this problem. So let's do just that. Let's reverse this array several times without actually calling the reverse one. Let's just do it from scratch. We're going to need some variables in order to do this. First up is a temp holder variable. Then we have a start and an end integer variable. Start is set initially to 0, end is set to the last index of the array, num size -1. And of course, finally, we have our usual fix for k, ensuring that it is going to be within the array size by using modulo here. Next up is a while loop that's going to handle the first reversal. This is going to reverse the entire array as shown in this example here. So while our start position is less than our end position, we want to essentially do a swap. Temp holder becomes equal to whatever the value that nums has at the start position, which is initially 1. That frees up the start position to be replaced by the value at the end position, which is 8. And then of course the nums at the end position is freed up to equal what the temp holder is. So 8 and 1 switch positions. Then we increment up start and decrement down end. And we do that until we get through the array. Now, if we're doing this all within one function and just doing it raw code then we would need to reset our start and end positions. Start is still 0. End, however, is going to be until right before k, i.e. k minus 1. And then the second reversal can take place. And this while loop is exactly the same as this one. Finally, we have to do essentially this entire step again, resetting the start and end position. Start this time is equal to k. End is now the end of the array. And then again, we call this while loop for the final reversal from k all the way to the end of the array. And then after this while loop, we have our final answer. Now, as you can see when I click buttons here, this does work. Judging, finished, and I can hit submit button, and it will pass. We can get lovely green text. But as you might be screaming at the screen right now, this is a horrible, horrible way to write this kind of code. There is a ton of redundancy here within the while loops, because the while loop, as you can see, changes in absolutely no way. The only thing we're changing is the start and end positions. So if you ever have code which has a huge amount of redundancy in it, where you're calling a specific amount of code lines over and over and over again, a better way to do that is to simply stick that code in its own function. And every time you need to use that set of code, you just call the function. So let's eliminate this redundancy and create our reverse function. Okay, first things I've done is, instead of this void function going all the way to the end, I've capped it here. So at this point, it only has our variables in it. Now I made a new function here that I, of course, name reverse. It's void, it's not going to return anything. And it takes a couple of parameters. It'll take the array, it'll take an integer variable named starting place, and it'll take another integer variable, ending place. And so far, everything else, all of these while loops, have been stuck in it. What we need to do now is figure out what needs to go where and what we can start eliminating. For elimination purposes, let's go ahead and get rid of all of this repetition. Bye-bye. Now, we have this while loop here. But this while loop is referencing temp holder. So instead of temp holder being here, it's going to go in the reverse method. The final thing I have to change within this function is, instead of referencing start and end, I'm going to reference the starting place and the ending place, the parameters of this function. With those changes, this function is complete. Now all we have to do is go to our rotate function and call this function here with the appropriate parameters. Here's the first reverse call. We put in our array, we put in our starting place, 0, and we put in our ending place, which turns out to be num size minus 1. Next we just call it again. Same array, same starting place, but this time our ending place is k minus 1. And now finally, our third reverse call, still the same array. Our starting place this time is k, and our ending place has now gone back to the end of the array, num size minus 1. And as you can see, by directly inputting what our starting and ending place is, we really don't need these variables anymore. All we need is to make sure that k has been adjusted accordingly. And with this, we have a much more succinct, much more maintainable bit of code in order to accomplish the exact same thing. Because as you see here, we run the code, we get pending, judging, and finished. This answer matches this answer. We do the big blue button push. We get more pending and judging, and we get green text this time too. So it works, and with this methodology, and if we ever needed to make a change to the logic of this while loop, we could simply do this, and every time we call the reverse function, it's automatically going to have those changes in place. Whereas in the previous methodology, if you have lots of repetitive code and you want to make a change to that repetitive code, you'd have to manually change it in every single place, which is a massive pain to do. So this is why reducing code redundancy is a very, very good thing. Now, with all that said, let's move on to doing some time and space complexity analysis here. Well, in this situation, we only have an integer variable here, constant space. So our space complexity should be big O of 1. Our time complexity is going to be dictated by this while loop. And although we call it multiple times here, the while loop is just going to be going through the array in a linear fashion. It's going to be dependent on the size of that array as a result. So it's going to be a big O of n time complexity, where n is equal to the size of the input array. Last thing to do is check where our rankings are. So here we have a runtime of 80 milliseconds. It's way off of the curve here. It'd be interesting to see if I did this again, if it would be ping-ponging in nature, so I'll probably do that after we do a quick look. Our memory usage, however, is way up here. Now, in a previous solution, we were somewhat down here because we made a new container, and thus we had larger memory usage. But since this is an in-place solution, our memory usage is probably going to ping-pong around this distribution instead of being around here. But let's go back to the problem and see if I submit this one more time. Let's see if anything's going to change in that ranking of the time. Yeah, okay. So here we're now well within this distribution. So as I said before, take these rankings with a grain of salt, because depending on the problem, you can ping pong quite a bit. And here we're pretty much in the same place we were. But I still wouldn't expect this memory usage to ping pong so much that we would ever get down here. So it should be able to distinguish, say, big O of n space complexity here versus big O of 1 space complexities around here. Now, this was a way to solve it via a series of reversals, but there's one more solution that I want to show. Instead of using a series of reversals to eventually get our values into their correct position, what if we try to do this as efficiently as possible and immediately move each value to exactly where its new shifted position is going to be? So let's bring out my handy dandy whiteboard again. And let's say we have this kind of array. Well, what would that look like? We're going to use a k of, say, 2. So 1 is going to end up where the 3 is. The 3 is therefore going to end up where the 5 is. The 5, since it wraps around, is going to end up where the 2 is. The 2 is going to be where 4 is, and then 4 finally wraps back around and goes where the 1 is, and we're back at the position that we started this from. So this is more of a cyclic leapfrogging approach. Now you could have this example here, where in your leapfrogging, you go through and touch every single array value, and you wind up right where you were at the very beginning. One loop is all it takes. However, instead of this array, what if we had this array, still with k being equal to 2? Let's see what happens here. Well, just like before, 1 is going to move where the 3 is. 3 is going to move where the 5 is. But now, the 5 is going to move 2 places. So, shift 1, we get to 6, shift another one, it wraps us all the way back around to 1. So there, we have a closed loop. But instead of going through the entire array, we've wound up back where we began after only some of the values have moved. So if we still have more values to look at, we need to shift our position from the beginning index to index being 1, and then just start a whole nother loop. 2 shifts to 4, 4 shifts where 6 is, And of course, 6 shifts back to where 2 is. And thus, after that loop, we've seen all of the numbers. All of them are in their right places. So now we can end. And it's this methodology that we are now going to use to create our last solution. Now that we have our methodology understood of how we're going to attack this problem, what pieces of information do we need in order to create that code that does this? Well, we need a counter because we need to keep track and make sure that we have seen every single value that is present in this array. So that's going to be one integer variable we need. Now, we also, in our leapfrogging approach, need to be able to know the current index that we're on. We need to know the current value at that index. We need to know the next index, it's like destination index. We need to know the value at that destination or the next index. We have to store all those 4 things. So those are going to be our relevant values. And as we saw with that second example, we're going to have a loop that handles that cyclic travel. We will also need to have a separate loop that in case that cyclic travel doesn't travel over the entire array, it will shift the index up by 1 and then pass it over to that loop that is handling the cyclic journey. So with all of that information, let's go down here and start the coding process. First up, we have the count variable, initially set to 0, and of course our tried and true k correction using modulo. Next up is the beginning of the loops. This for loop is going to be what shifts our index if needed. It's going to have our index start at 0 at the beginning of the array, and its ending condition is going to be as long as the count is less than the size of the array. In other words, go as long as we haven't seen every single value of the array. And then within this for loop, we start creating 2 of the other variables that we're going to need. Current index, which is just I, and current value, which is just the value at I in the nums array. Now we have the loop that is going to handle the cyclic journey. And you notice that instead of a for loop or a regular while loop, this is a do while loop. And the reason it's a do while loop is because of the condition here. The condition is we want this code to execute as long as our current index is not equal to I, because we want it to move along in its cyclic journey and we want it to stop once it wraparounds and comes back to where it started, i.e. the current index is again equal to I. But the problem with that condition is that if this is just a regular while loop here, the while loop is never going to execute because our current index has to start at I. To get around that, you use a do while loop. And the code here is guaranteed to execute. It's going to do the execution of this code at least once, and then it's going to look at the while condition. And of course, as you'll see soon here, this code moves the current index to something so that it isn't equal to I anymore, which means this entire thing will do what we want it to do. Cycle around until it comes back to where it started. So let's go over this code a bit with an example from our whiteboard, just so that we can track what's going on after each code line executes, so that we can make sure it's doing what we want it to do. So here we have our array, we have our k value, we have our count variable at the beginning that equals 0, and then we start into the for loop here. That gives us a current index value here and a current value here. So current index is equal to I is equal to 0 at the start, so put 0 there. And current value, the value at index 0 is 1. Now we go into the do while loop. So next index is set to current index plus k, well, 0 plus 2, and then we do modulo num size. Now 2 modulo anything bigger than 2 is just going to be 2. So next index equals 2. Next value, the value of the array at index 2 is 3, And now we can start messing with things, since we've assigned everything so far at this point in the code. Next up is nums at next index is going to be set to what the current value is. So here, our current value is 1. So we're going to go look at nums at the next index value of 2 being replaced with our current value, 1. So 3 becomes 1. And that's fine with us because our next value variable still has a record of that 3. And that record comes into play because we're going to now set our current value, which used to be 1, to our next value. So current value here becomes 3. Current index now becomes next index. So next index 2, current index was 0, now it's 2, and our count goes up. Now when we check this while condition, our current index no longer is equal to 2, so we continue in with this loop. When these lines execute, it's going to turn next indexed to 4, 2 plus 2, current index 2, k 2, so next index becomes 4. Next value becomes 5. That 5 is replaced with the current value, 3. Current value becomes next value, and current index becomes next index. Now when this code executes again, next index becomes 4 plus k, 2, so it becomes 6. But 6, when divided by 6, is going to be 1 remainder 0. And with modulo, we only care about the remainder. So that index is going to wrap back around and turn back into 0. So next index is that. Next value records that 1 that's still there from the beginning. Then the replacements happen. So num's next index here is set to the current value, which is 5. And then current value becomes next value, which in this case is something that we've already completed, and current index becomes next index. But now our while condition recognizes, hey, we've come back to where we've started. Current indexed is now equal to I again, so this loop stops and returns control back to the for loop here. The for loop has I increment up. Now I from 0 is equal to 1, and current index is set to 1 now. Current value is then set to 2, and then it sets up for this do while loop to continue with a cyclic journey for the next set of numbers. So 2 will replace where this 4 is, 4 will replace where that 6 is, 6 will wrap around and be replaced where the 2 was. Thus, this code is indeed executing as we would imagine it. So with that, let's go ahead and try and see if I've made any mistakes. So far, no. We get what we anticipate, so let's go ahead and do the full shebang. Pending, judging, green text. Very, very lovely. Okay, so as always, before we hit this button, let's go and look at what the complexities are for this solution. We have several variables here at various places, but all of them are integer variables. They're all going to take up constant space. So we haven't made a new vector, we haven't made a new list or map or any other variable container. So as a result, this solution is still big O of 1. Constant space usage. Now, although you might be looking at these nested loops in terms of time complexity and think, hey, nested loops, big O of n squared or n times m, that kind of thing, right? No. As we saw in our examples here, this for loop and this do while loop are essentially dependent upon each other. They work in tandem with each other to go through the array only once. How many times this for loop runs will be dictated by how many values this do while loop can get through. If this do while loop can essentially run through the entire array, it will increment up the count to the point where it can register that, hey, we've seen all of the values present, count is now equal to this array, so this for loop never has to run again. In contrast, if this do while loop only gets through part of the array, the for loop can shift the index so that this do while loop can run another cycle. Because of that dependency in how they function, these loops still only have a big O of n time complexity, linear time. Now let's see where we are in the rankings here. So runtime has popped up here, and again I'd probably anticipate it ping-ponging around the distribution in various ways. And our memory usage is still here, indicating it's still in that big O of 1 distribution here instead of big O of n distributions. But we do have a couple of extra integer variables compared to the last one, so it makes sense if it might be a little lower. Of course, that might be concealed depending on, ping pong mechanics. In any case, that was how to solve the rotate array problem via several solutions. I hope this video helped you out in some way. If it did, consider subscribing. And with that, I will wish you happy coding and to have a nice day.